It is a great pleasure to to present Mohammed Manji. Yeah, now I pronounce it. You're from Warwick University. Okay, he will speak about ordinary, ordinary and non-ordinary conjectures in Iwasawa theory. So.
Thank you very much. Before I start, I'd like to thank especially Daniel, but all of you here for inviting me here and for being present here today. I'll outline the plan for my talk, and maybe you know it's split into two parts with a coffee break in between. So the plan is this. Section 1, I'm going to discuss the setting for modular forms. So maybe this will be something that more of you will be familiar with. So just the Iwasawa main conjectures. And I'll discuss this case for ordinary modular forms. And this will be a big part of the talk. I'll go into details here, and then in later sections, maybe we'll just refer to this, this first basic setting. And then section 2, I'll discuss non-ordinary modular forms. I'll define this as well in the right time. So I know you've had a lot of talks to do with automorphic representations, modular forms. We're going to start off with this, and then later, after the coffee, we'll go to discuss representations of the group GU21. Okay, but everything that I'm going to say here is really going to be following the pattern here. So this is why I'll focus on the modular forms case, and then this is work that has already been done. So largely done by Chris Skinner and Eric Oban in 2006. So I'll write that. This is the work of a lot of authors who I'll name a bit later. And then this, from here on, this is recent, current work. Okay, so we're going to discuss GU21 representations, and then we're going to do the same thing as we did in the first part. We're going to discuss ordinary conjectures, and we're going to discuss non-ordinary conjectures. So hopefully with this pattern, when we get to this section, it will be easy to see how these two different theories behave. So I'm writing IMCs for Iwasawa main conjectures. Hopefully that will save a lot of time. So this is when we're going to discuss the case for split primes, and it is the same as ordinary. Yeah. And then we'll discuss for non-split primes. Okay, so this is just the plan for today. And yeah, like I said, that maybe we focus more on this part, and a lot of ideas will come from this section. But this is recent work here. So a lot of questions will arise here. And then maybe if any of you have experience with working with unitary groups or anything like this, I'd love to hear ideas about anything in this talk, in this part of the talk. Okay. Do we split the board in half? Is that a good idea? Let's do that. Good. Okay, so let's start with section 1. This is the Iwasawa main conjectures for order. So, okay, let F be a modular form. And we have its Hecker polynomial. which you define as x squared minus apx. So here we have f is the to the n expansion, and this is the AP, so the pth term. And then the constant term is something like this. Okay, so this is some character, chi, which is the Nevin type of the mode, but we don't really need to worry about this. For now, I'm just writing it for complete. Yeah. Okay. So we have this polynomial, the Hecker polynomial. So okay, forget about this chi, but we care about this term. So the AP is it's the eigenvalue of the UP Hecker operator. And we impose this condition. Okay, so this has two roots, alpha and beta. And we know that the valuation of alpha plus the valuation of beta is equal to the valuation of the constant term, which is k minus 1. Oh, I should have said weight k. Okay. So what I mean by f ordinary is that one of alpha or beta is not divisible by p. So one of these roots is a p-adic unit. And this is what we mean by an ordinary modular form. But of course, because we have this formula, if this is valuation 0, this is going to be valuation k minus 1. So not, unless you have a weight 1 modular form, which we're not going to be thinking about, only one of these roots can have valuation 0. But often what happens if you have a non-ordinary modular form is that both of these are going to be non-zero. So I'm not going to discuss that setting here. I'll discuss it in section 2. For now, we just want to think about this section. So we'll just assume alpha is a p-adic unit. Okay. So we want to study this thing which I hope you've seen before, which is the L function. So again, this chi is the same character as here, but we don't really think about it. It just helps to generalize results. So this is the L function of the modular form. Okay. And why do we want to study this? Just one example, but I'm sure you've seen many examples of L functions and why they're important. So if f arises from, oh, okay, let's say, that's the right way to put this. Okay, if f arises from an elliptic curve, E over Q, so just by modularity, we have an elliptic curve which corresponds to our modular form f, which means, of course, k is equal to 2. Then we have the Birch-Swinnerton-Dyer conjecture. Which says this, that the rank of the Q rational points of the elliptic curve is equal to the order of vanishing. I'm now dropping the chi. Just I might do that sometimes. Like I said, we don't worry about the character, but the order of vanishing at s equals 1 of this L function. Okay, so the L function is a very important thing to study, and the motivation for this talk will be we want to understand why this L function contains information like this about arithmetic objects. But this L function is a complex analytic function. So as we have it right now, we don't have an algebraic way to study this L function. Okay, so to study it algebraically, we don't look at the L function, but we look at the p-ádic L function. So I'll be lazy and I'll often just write LPF and ignore the rest of the notation. Okay, but actually this is a bit more. This is dependent on F, the Nebben type character, and also your choice of alpha here. So yeah. And of course, remember that we set F is ordinary, so we choose alpha, which is a p-ádic unit. Okay, I'll explain why this is important. Okay, so are we familiar with p-ádic L functions in general? Would you like me to say a bit more about this? Okay, I'll try and say a bit.
For example, you can say where is below the variable s.
Hmm?
You explain what is the variable s.
Okay, yeah, I'll do this. Okay, so I guess the key point is this LPF, it links to the L function in the sense that it interpolates values of LFS. So for example, we have the formula and I'm keeping this alpha because it's important in this formula, is equal to alpha minus n times, okay, I should say what n is. Okay. This is a Dirichlet character modulo p to the n. So this is just the choice of Nematibus, but actually often we can think of this character as the trivial character. So then, but for this case, we let it be a Dirichlet character modulo p to the n, and we get this formula. I'm going to write G here for a Gauss sum, which we won't worry about because it's invertible. So we don't care about this. Okay, so we have this formula that the p-ádic L function at integers in a certain range. I don't remember the range off the top of my head, but so let's say so there's a certain range which depends on the modular form. 1 and k minus 1. Okay. That makes sense. Okay, so at integers in this range, if you plug in this value of s, then the p-ádic L function, which normally takes values in, I guess, ZP, because it's a measure over. So I'll discuss the measure thing in just a few minutes. So, but we think of this as a measure over ZP, and if you have this formula which compares it to the original L function. So this is something called a period, but again, we don't really care about this. We don't care about this. This is p to the n times some integer. So we understand this part well. Really, it's just this term now. So, okay, I'll write this in shorthand. LPF grows like alpha to the minus n, LFXS. And you can change, you can look at modular forms of different characters, chi. So because we're looking at this ordinary case, when f is ordinary, alpha is a unit. So VP alpha is equal to 0, right? Which means alpha is invertible. So this gives us okay. This tells us that LP is bounded, right? As the n increases. Can I use black? Yeah, absolutely. I didn't actually see the black earlier. Which bit is not clear to see?
No, it's fine. You're just...
Oh, it's getting worse. Yeah. Okay. Yeah, no problem. Okay. So when f is ordinary, this alpha is a p-adic unit, and therefore you can invert it. So this LP is bounded as a distribution. So I'm going to revisit this, what we mean by distribution, in just a minute. And I guess that's the key thing. This LP compares to the L function, but the choice of this root alpha is actually quite important. So when f is non-ordinary, LP is not bounded. Okay. Okay, does this justify why we just want to think about the p-adic L functions? So the p-adic L functions compared to the L functions, but they have more algebraic properties. Okay, good. So what do I mean by algebraic properties? Okay, so why is LP better? So one answer which I can give you is this. LP lies in a ring, a certain ring which I'll define just now. Which we understand. Okay, so whilst the L function is a complex analytic function, so we can consider it in very complicated rings, whereas this LP lies in a certain ring which we understand quite well. And I'll define this ring just now. This is the Iwasawa algebra. Okay. So we'll have a group gamma, which is equal to the Galois group of what I define as this: QP infinity over Q. So QP infinity is the max unramified, it's the max extension of Q unramified away from P. So it's unramified at all primes Q not equal to P. So this is a Galois group with the property that okay, this is P minus 1 different copies of ZP. But actually, I'm going to be a little bit, I'm going to make this a bit simpler. So instead of using Q, maybe if I attach just the Pth roots of unity, then this is no longer equal to p minus 1 copies of zp. This is equal to zp. Okay, so really we should be thinking about q, but just to make things simpler, I'm getting rid of all the roots of unity. So this is a little. If you look at a paper about Iwasawa theory and you see what the results look like with working over Q and working over Q with the roots of unity, it's much more simple this way, and the theory actually doesn't change. So I'm doing this for your benefit. I hope you trust me on this.
There is maximal abelian extension.
Yeah, sorry, yeah, of course, maximal abelian. Yes, good point. Yes, so we think of this group gamma, which is actually just ZP, but we do this because then we have a Galois action. Okay, and now we define the Iwasawa algebra. So Iwasawa algebra is this lambda. So lambda is equal to lambda subscript gamma, which is this group ring. But then, because we know what gamma is, it's just ZP, and ZP has one topological generator. So it's got a topological basis of size 1. We can also say this is isomorphic to this power series ring. Okay, I think maybe this bracket shouldn't have the double. I don't remember what the right, but I think group rings have double as well? Yeah. Okay, they both have double. But okay, this is now not a group ring. At the bottom, this is a power series ring in one variable. Okay. So we've constructed this Iwasawa algebra, which really is just a power series ring in one variable over ZP. And I've claimed to you that this p-ádic L function, which at the moment maybe we don't know so much about, it lies in this algebra. Yeah. So it is worth just me reminding you that, remember we said that when f is ordinary, our p-ádic L function is bounded. And when f is non-ordinary, the p-ádic L function is unbounded. And it's because we had this alpha to the minus n term. So if alpha is a p-ádic unit, it's fine, we can just invert alpha. But if alpha isn't a p-ádic unit, then as n gets large for some choice of character, you invert by something arbitrarily big. So you can get terms with as big a denominator as you want. So this L function will be an unbounded distribution. Okay, so we're going to be thinking about the Mahler transform, just briefly, in order to justify to you that the p-ádic L function lies in this algebra. So also, maybe it's worth saying, a lot of the things that I'm discussing in this part of the talk, you'll find the details in the notes of Chris Williams and Joaquin Rodriguez Jacinto on what is it, p-ádic L functions? I think p-ádic L functions in Iwasawa theory or something like this.
It's not very well done.
Yeah.
I don't remember the title, but it's in this page.
It's in, yeah, so there's two parts, and really I'm using facts from both of those parts. So including this, the Mahler transform. And the Mahler transform is this correspondence between ZP valued bounded distributions and power series over ZP. Okay, but this is our Iwasawa algebra. So the Mahler transform tells us that if we have a bounded distribution, so let's say f is ordinary, and therefore our L function is bounded, then this has a unique image in the Iwasawa algebra, which we're also going to call LPF, just to avoid having too many different things to write down. But yeah, so the Mahler transform gives us a way of thinking about distributions and power series as the same thing over ZP, and therefore we think about our bounded p-adic L function as an element of the Iwasawa algebra. Okay, so why is LP better than L? Because LP lives in this Iwasawa algebra. Okay, so yeah, maybe this is, does anyone have any questions about this? Okay, then let's carry on. So now we know that it lives in the algebra. This still raises the question: how do we study LP algebraically? We now have the tools of studying this thing. So this is our aim. So we want to find an ideal I in lambda with I is being generated by the p-adic L function. Okay, when I say find an ideal, I mean we want to, I mean we can just write this, but we want to find another way of constructing this ideal such that it's generated by the p-adic L function. So this is what this is what the Iwasawa main conjectures.
Maybe describe.
Okay, yeah, describe is a better word. We've already found it. Describe. Okay. So we'll write this as follows. So starting with a modular form F, and this is weight K and over Q, just for simplicity, but you can change, this sort of ideas work with modular forms over, I think, imaginary quadratic fields, CM fields, and there's a lot of generalities, but I will just stick with this case. You can attach to it a Galois representation, which we call VF, and it's k-dimensional. Okay, so the reason I want to do this, because it's GL2, isn't it? Two-dimensional. You know, I wrote K, but this doesn't make sense. This is 2. So you get a two-dimensional Galois representation, and this is something which, unfortunately, I'd rather not do. But it turns out when we look past modular forms to higher groups, really the right way to think about things is in terms of automorphic representations and Galois representations. So I'll come to that in a later section. But for now, given our modular form F, we construct this two-dimensional Galois representation. And these sort of construction come from the Langlands program. So there's this very general machinery of taking some automorphic thing and giving a Galois representation. So what I mean, by the way, by this is, I mean, this is a two-dimensional vector space over QP, over QP, but with an action of the Galois group. And in our case, the Galois group is going to be this one.
The Galois group is the absolute group. Q bar over Q.
It is, but the way we state this, it just turns out that the action of the absolute Galois group over this is trivial. Okay, but maybe technically to define a Galois representation, you're right. Okay, so what do I mean by Galois representation? I mean vector space over QP with action of the absolute Galois group, that's true. Okay, so you might ask, what does this VF look like? But actually, it's not so easy to write down. There are different ways to describe it, and we'll look at a few of these. But really, there's a reason we want to do this, and it'll hopefully become clear, because I'm hoping after we discuss these technical things, I'm going to draw a nice picture, and then maybe we see the overall, the shape of this theory. Okay, so, okay. So in this case, the VF is constructed by a certain quotient of the Ital cohomology of the modular curve. So I'm writing this just so you have an idea of where this comes from, but this is not going to come up again in the talk. So don't worry so much about this. But what I really want to tell you is that this construction of a Galois representation, which is this is a two-dimensional vector space, with a Galois action is actually not so easy. It's some quotient of some complicated cohomology group. But thankfully, this work has been done. Somebody has said, given a recipe, given F, you get this Galois representation VF. And this is a unique choice for each F. Okay, but now we've done this, we can consider cohomology of VF. Okay, so I mean, there's a lot of work which goes into describing these cohomology theories, and I really don't want to stay too much on this part. So I'll define the right cohomology things, but really, the important thing is not the definitions. The important thing is that given F, we get a certain group with the right properties, and the property is that this cohomology group is going to be. So we're going to. Okay, well, these cohomology groups are going to be modules of this Iwasawa algebra. So this is our motivation. We have an algebra which the p-adic L function lives in. We just want to find some way of constructing certain modules over that ring. Okay, so the cohomology is this. It's the Iwasawa cohomology of this earlier Galois group. We had gamma and VF, which we described to be the inverse limit of the cohomology of finite Galois groups. Whenever I talk about cohomology, I always see unhappy faces in the audience. So I want to really, I'm writing these down for if any of you are familiar with cohomology, then this section is for you. But if you're not, then at the end, we just spit out some group, and you don't need to worry about how we got this group. We just need to know that it has information about the modular form, and it has the structure of a lambda module. So we consider this group, but this is unfortunately infinite dimensional, which is not a good thing, because when we, okay, you know why this is not a good thing. We want something finite dimensional. We want to understand what the dimension is. So what we end up wanting to do is we cut out some piece of this. We take some carefully chosen finite dimensional piece of this big thing. Okay, so we define H1F inside this, and this is the classes of this thing such that which are unramified at primes not equal to P. And then we have this extra technical condition at P, which is that these classes are crystalline at P. But really, this notion, which I think is not useful to define right now, it's something similar to being unramified. So. So I'll put this in quotes. Crystalline at P. If any of you are familiar with p-adic Hodge theory, maybe you know why this is the right thing to think about. But if you haven't seen this thing, crystalline is. I guess the problem is when you're thinking about a p-adic Galois representation. So this choice of P is fixed from the start. Remember, we fixed P so that F is ordinary at P. When you're thinking about ramification at primes away from P, this is fine because we have an inertia group, and then we just think about how the class behaves when we restrict to the inertia group inside the Galois group. But when we're doing this at P, we no longer have this inertia group at P because of our Galois group, our choicer group. So we have to think of some more complicated thing to replace the notion of being unramified. That's what this is. This is some complicated replacement for unramified. But really, I want you to think about this as being unramified. I just didn't want to write it down because I don't want to lie, at least not so. So obviously, okay. So we think of these classes which are unramified in this sense, and this turns out to be finite dimensional. So this is a finite dimensional, as I said, lambda module. Okay, good. Now this choice of a subgroup of this is called a Selma group, but this specific choice is called the Bloch-Kato-Selma group. So you see this appear in the literature all the time, but we can define other conditions. Maybe we get a slightly different chunk of this big cohomology group, and they're also called Selma groups. There's a lot of different choices. This turns out to be the right choice, but in the theory, when we look at things which are not modular forms, sometimes we need to look at other groups. So this notion of a Selma group is very important. I mean, maybe some of you have heard Selma groups when looking at the theory of elliptic curves. Okay, I'm seeing some nods, that's good. Now, when F is coming from an elliptic curve, this actually turns out to be the Selma group of the elliptic curve. So then this language is not a coincidence. It's motivated by this Selma group of an elliptic curve. Okay, so Bloch-Kato-Selma group, this Bloch and Kato will come up later when I talk about the Bloch-Kato conjecture, which is very linked to the Birch-Swinnerton-Dyer conjecture, which we had earlier. So what I wanted to say is, why is this a lambda module? So remember that lambda is this thing. It's ZP, double brackets T, but it's also ZP, double brackets gamma. So to have a lambda action, we really want a compatible ZP algebra structure and also group action of lambda. So this automatically comes from this cohomology group. Because it's a cohomology with respect to this group, we get the group module structure. And because we've taken an inverse limit over finite groups which look like p-power things, we get the ZP structure. So the reason it has a lambda structure is very natural from how we've constructed that. Okay, but for now, all this complicated cohomology stuff aside, we will refer to it as H1F. This is this lambda module which has come from F. Okay, do we have any questions about this? We're getting closer to the picture. So maybe, is it worth starting to draw the picture? Yeah, maybe we start to draw the picture and then we fill in the gap. Is there a clock in this room, by the way? Maybe look. Okay. Okay, so what have we done so far? We've gone from F modular form we've done this Langlands machinery to get VF a Galois representation. Then we've taken its cohomology. Can you read this? It's a bit small, sorry. To get this H1F, which is a lambda module. Okay. And then, now there's only one more step in this machine. And what we end up we want to have an ideal of lambda. And then we're hoping this whole thing will give us the p-ádica L function. Okay, so we've seen this construction, and now there's just one more step. And because remember, our aim is to describe this ideal, which is generated by the L function. Okay, so the question now is, how do we get from lambda modules to ideals? So I'm going to define this general notion that given a lambda module M, so this is, let's say, category of lambda modules, we define the characteristic ideal of M, and it's going to be this. So there are two cases. The first case is nice and easy. It's 0 if M is not torsion. If it's not a torsion lambda module. By torsion, I mean that for any element of the module, there's some element of lambda which sends it to 0 under the group action. So actually, most lambda modules will not be torsion. So this is 0 almost always. But we don't want the p-ádica L function to be 0. So, this is the case we don't want to be in. And if it's a torsion module, we describe it as this. So we consider the prime ideals of the Iwasawa algebra of height 1. And we have this product where we take, I'll write this out and I'll explain it. Okay, so we localize, we define it as some product of prime ideals, and the exponent, which it's not so important what it is, but I'll describe it anyway. You localize the Iwasawa algebra at this height 1 prime p, and then you tensor product M by this lambda subscript p, and then LP is the length. So LP equals the length of gamma p module. Okay, but this exponent is not important. I just wanted to show you there is some explicit description. The point is we define it as a product over the height 1 primes of lambda. So thankfully this works nicely because lambda has a very nice structure of prime ideals. To understand the structure of prime ideals, this is work of Iwasawa. So if any of you are more interested in this, I think it was the 60s that he worked on it, and he really describes explicitly what the prime ideals look like. So this is a well understood thing, something you can write out.
A question? So how you prove that this one is the proof of this is finally generated? You wanted to say there. When the dimension you need finally generated.
Yes. How do you prove that? So, in the general machinery of Selma groups, these things do turn out. Okay, if you have any Selma group which is constructed like this, where you have a condition at each prime, but for almost all primes, the condition is the unramified condition, this is going to be finally generated. It's a general result. Now, I know I've seen this in Joël Belaïch's notes about the Bloch-Carter conjecture, but I don't know whose result this is.
For any color representation, very general.
It's a very general result. So yeah, the key thing is this unramified part. If we impose that the class is unramified almost everywhere, and then the set of these elements is going to be finitely generated. So yeah, so this, I guess this choice is not so relevant for that, for the finite. This choice is relevant for the result, the Iwasawa main conjecture, which we'll come to soon. Yeah, any more questions? Okay, so what I've given you just here is a way to get from a lambda module to, this is an ideal. So this is an ideal of lambda. It's an ideal because we define it as this product of certain prime ideals. Okay. And yeah, this is really motivated by the classical setting of Iwasawa theory. So Iwasawa's original work was not looking at modular forms. He was looking at the GL1 setting. So he was looking at the p-ádic zeta function rather than the p-ádic L function of a modular form. So this definition, I can't say to you that it looks like the right thing from here, but it's motivated by Iwasawa's original work.
You can think maybe in this, when you do the parallel between the Iwasawa algebra and Z, just the integers. So you have the structure theorem for modulo or Z. When the model is torsion, it's just it's well described.
Oh, I see. Okay.
And this
From
this way, it's a good parallel to understand it.
Okay, that's nice. I hadn't thought of this.
Okay, so this the idea is this is a way of this is an invariant you can attach to lambda modules, and I guess like Daniel said, it's very classically motivated. Okay, so let's add this. So we take the characteristic ideal, and then we get some ideal, which I'll call I. Okay, so now I'm going to state the Iwasawa main conjecture for ordinary modular forms. And I think I'm a little bit over time. Okay, we'll have time for this. And then I wanted to discuss non-ordinary things, but we can let's see, we can push it after the break. So the theorem, which is, like I said, it's Skinner-Urban 2006. So we want F to be a weight k greater than or equal to 2, nu form, cuspidal, and an eigenform. Okay, and these are all reasonable conditions, because to say it's an eigenform, the cusp forms have a basis of eigenforms. So this is a reasonable thing to expect. Nu form is just something which always appears in these results. We want we want to choose the level optimally so that our modular form is a nu form. And I don't know why the cuspidal is a necessary condition, but actually it turns out even when we look at past the GL2 case, we discuss automorphic representations. We will need to look at cuspidal things. So this cuspidal thing is a bit crucial here. But so F is this sort of modular form such that F is ordinary at P, of course. And then we assume some minor technical conditions, which I'm not going to say, because it'll really detour from what the talk is. But for example, we want some H0 cohomology groups to vanish. And if you ever work with cohomology and you know that you get these long exact sequences, it just helps. The right statement is in their paper, and this will come up again in the second half of the talk. Another condition which we have is P is greater than or equal to 5. So we ignore 2 and 3. P doesn't divide the level, of course. That's something we said at the start. And then we want the modulo P representation to have a big image. So we do, for example, we don't want it to, it doesn't have to be surjective, but we want it to be not so far from being so. So this is just a technical, the mod P representation. So do you want me to write out what it looks like, or?
That'd be awesome.
Okay, so you have V corresponds to some representation, which we write rho, which goes from the Galois group to GL2 QP. Have I got these in the right order? Yeah, okay, I think so. And then you have the mod P rep. Yeah, sorry, yes. And it's GL2 because it's a modular form. And then we get the modular P representation, which goes from, it's just this mod P, so GL2 FP. And we don't need this to be surjective, but we want this to be close to being surjective. Okay. So I think when people were originally looking at this, they assumed surjectivity, but actually it's not necessary. You can weaken this a bit, but you can't have this, for example, being the 0 map. Then your results won't work. So I'll put this as a... These sort of things are called big image conditions. And you see them, they're in this sort of literature, you always see them referred to, big image. I've seen sometimes recent results have weaker statements. So they say very large image or enormous image. And when someone says that, it's a weaker condition than big image. Okay, so we assume F is this sort of modular form, and we assume some minor conditions. Then the characteristic ideal of this gamma. So I said H1F, but actually I wasn't being completely honest. We take the Pontryagin dual of H1F, so the dual module. And this is equal to the ideal generated by the L function.
So for that, I think you are supposing
That this Montreal or this dual is torsion. So
this module is torsion.
yeah.
Yeah.
So they prove in this paper that it's torsion.
They prove that it's torsion.
Proved before maybe by Kato.
Oh, it's certainly proved. So actually, when you have the Iwasawa main conjecture, yeah, you need... There's certain statements that come before this. So one of them is that this is torsion. So you're right that I should write H1F is torsion.
No, I think the dual is torsion.
Oh, yeah, okay, you're right. Then... Okay, no, that's absolutely right.
Yeah, but the proof is torsion is Kato maybe, no? Something too. Or using these earlier systems.
Yeah, so I think you're right because Kato proved this divisibility.
Yeah,
so I think, and you need it to be torsion to define this.
Yeah.
So I think you're right in his asterisk paper.
Yeah.
Yeah. So you're right actually because Skinner and Urban only proved the other direction in order to complete this statement. So maybe I should also say Kato. 2002, did you say?
I think so. He announced this 8 years before.
Okay, yeah. So there's two because it's an equality of ideals. There's two directions, and then Kato did the first direction using the method of Euler systems, which I won't go into, but it's super relevant to the next part of the talk, but behind the scenes. So I'll try not to talk about them, but and Skinner-Urban proved the other divisibility, and therefore you get an equality. Okay. So this machinery that we've come up with, we take this Langlands-style construction or Galois representation, take its cohomology, and then take the characteristic ideal, this actually just gives us a formula for this L function. But it's very surprising because none of these steps are analytic in any way. We want to think of the L function as a distribution, but all of these steps are quite algebraic. Okay, and just before, maybe we'll pause after this, but I wanted to just say a little bit about how this links to the Birch-Winterton-Dyer conjecture. Okay, so if f comes from an elliptic curve E over Q, but actually we don't need this condition. We can actually do this for general f, but I'm only specifying this so that it links to the Birch-Winterton-Dyer conjecture. Then H1f is equal to the Selma group of E over Q in some sense. I know there are lots of similar definitions of Selma groups. There's one definition which is quite common, which matches this. And the corollary is this. Suppose E has good ordinary reduction at P, and then plus some technical assumptions which are exactly the same. But actually, we can take the technical assumptions, instead of taking them on VF, we take them to be on the Tate module of E. I don't know if sometimes it's called VPE. So the VPE, I'll write it here. VPE is it's something that looks like this, but then this is a ZP algebra, so we just have to tensor by QP. Okay, so suppose E has good ordinary reduction plus some minor conditions, then if the L function at E is non-zero, then we get the same period thing, which doesn't matter. But the p-adic norm of this inverted is equal to the size of the Shafarevich group, the Tate-Shafarevich group, or actually the p part of it really, times some Tamagawa numbers. So this is the conductor of the elliptic curve. Okay. But the crucial thing to take from this is that the L function is non-zero. This is conjecturally finite, and we actually just get a formula for it, the p-adic norm of the L function. So this is not giving you the Birch-Winterton-Dyer conjecture, but it gives you a step towards the Birch-Winterton-Dyer conjecture. Obviously, in order to get closer to the Birch-Winterton-Dyer conjecture, you need to prove this finiteness of the Tate-Shafarevich group. So somehow this Iwasawa main conjecture doesn't think about the finiteness of this, but it does take you in some direction towards Birch-Winterton-Dyer. Okay, so maybe we stop here, and then I said I would talk about non-ordinary modular forms, and then I would have the break, but maybe it's better that we'll continue with the non-ordinary setting, and then we'll maybe have less time to talk about GU21. Okay, so we went a bit over time on the first part, so I think we're going to skip the discussion of non-ordinary modular forms just to the end. Then I can talk about current work on representations of GU21. But it'll really follow a similar idea that we start off with maybe I'll change this diagram a bit. We start off with pi, which is an automorphic representation of GU21. I think you've had some talks and lectures this term about this semester about automorphic representations. We'll say a bit more about the definitions, but I hope this is something you're familiar with. You have some Langlands construction, and you come up with V pi, some Galois representation. So and you take the same cohomology, but then I'm not going to write H1F because technically this is a slightly different definition. I'm writing H1 with this squiggle over it. Oh, sorry, the one is up here, not down there. But you want to think of it the same way, and then we end up with an ideal. And then the question is, do we get a p-adic L function? So I'll leave this diagram up here. And so the one question is, do we get a p-adic L function? The second question is, what do we know about ordinarity? Do we, does this only work for ordinary representations, or do we need extra conditions? The answer is going to be that we need extra conditions, or we need one particular extra condition. So we'll come to this. Okay. Oops, we'll get that later. So section 3 this was. So we've missed 2, if anyone's wondering. 2 will come back at the end, and I didn't want to renumber them. So GU21 representations. Okay, so we'll come back to p-adic L functions at the end of this section, but we'll just discuss the definitions. So E is an imaginary quadratic field. E over Q, let's say. Imaginary quadratic extension. I've just realized that we used E over Q to mean the elliptic curve. So in this section, there's no elliptic curves. This is an imaginary quadratic extension. Maybe I'll just write over Q here. And we're such that of discriminant D, or minus D. So D is some positive integer, the discriminant is minus D, such that the square root of minus D has positive imaginary part. So just this is an imaginary quadratic field generated by this square root, but this square root has positive imaginary part. I mean, this statement is the same as saying we choose an embedding. And we choose this matrix. Okay. So maybe some of you have seen unitary groups where we define them as elements of some general linear group, such that they, when you conjugate them by some unitary matrix like this, you end up getting the same thing. This is exactly what we're going to define. So this, we're going to say for a Z algebra R, we define the R points of G. So G is equal to GU21. This is a bit of an abusive notation because often people write GU21 as the real points, but I'm going to just write them as this group scheme or whatever you want to. Okay, so we discuss it as the elements like this, G and V, in GL3 OE, but then we want to tensor by R because these are the R points, such that, GL3 of this times the units in R, such that if we take this transpose conjugation by J, this is equal to this is equal to this unit times j. Maybe worth saying that if we put SU21, then you get rid of this v. This v just becomes 1. That's really the same as saying that it would take the determinant of matrices to be 1. So this is how we define the group. This is not really so relevant to the rest, but I thought maybe it's nice to just see a definition. If any of you are unfamiliar, we see how this links to the modular forms case. Okay, so as before, we're interested in automorphic representations of G. But like in the modular forms case, these are automorphic representations of GL2. And we have this correspondence between modular forms and automorphic representations of GL2, which is quite nice. But now when we're discussing GU21, we don't really want to think about automorphic forms. This turns out to be quite messy and not the right way to think about it. We want to think about automorphic representations. Okay, so by this definition, we can think of it inside GL3 times this R cross, but the R cross doesn't matter so much. We really just think about them as matrices inside GL3. So we have something called Langlands functoriality. There's a lot of different names for this. But the idea is we have an embedding inside GL3 times GL1, but we ignore this part so much. Which means we have a correspondence between automorphic representations of this group, GU21, and automorphic representations of GL3. So I guess not L packets of automorphic representations.
Why is GL1?
Because I'm saying we don't need to think about it so much. I mean, it is times GL1, but I'm putting it in brackets. We just ignore it for now. So L packets of automorphic reps of GU21. And I don't like talking about things in terms of L packets. Maybe some of you don't, so we'll simplify this in a bit. But the Langlands functoriality gives us this correspondence in terms of L packets. So sorry, no, it's not one-to-one. So L packets of automorphic representations of GL3. Okay, but yeah, like I said, this is not so. You look at this and you think, well, okay, how do the actual representations correspond? So I'll mention this. So we have a one-to-one correspondence between. Okay. If you have a regular algebraic, it's going to be a long acronym, by the way. Essentially conjugate self-dual cuspidal representation pi. We write this as RAESCSDC. I know some of Daniel and Chris's work has a similar acronym. So these acronyms really do occur a lot, and it's because of this Langlands functoriality. You need to think of a way to match automorphic representations of one group to another one, and the way to do this is to impose loads of conditions. So this is an RAECSDC automorphic representation of GL3 pi, and this gives us a unique. Well, this gives us an L packet of representations in GU21, but to choose a unique element of that L packet, we impose the condition of a globally generic cuspidal and we'll call this little pi. You can ignore all of these words, but what I'm trying to tell you is that these words give us a way to get from a certain type of automorphic representation of GL3 into a unique choice of representation of GL1 or GU21. And what this means is that actually we just can do everything with GL3 representations, which is significantly nicer. And this sort of thing is done for a lot of unitary groups, symplectic groups, etc. We want to work with GLN representations because each L packet has a sort of distinguished choice of representation. And then we just add, I mean, the conjugate self-dual comes from this, because if you dualize this and then take the conjugate, it becomes itself. So all of these are, if you stare at them long enough, they're reasonable conditions to impose. We can guess what they are if you're an expert in the field, but I'm not an expert in this. I just know that if you put the words, then this works. And then to get a one-to-one correspondence, you add another adjective. You add non-endoscopic. Okay. So this is how we think about GU21 automorphic representations. We think of GL3 automorphic representations with a lot of different properties, but yeah, and this is also this is a big part of the Langlands program. And then, well, remember what we did before we had this Langlands construction of taking an automorphic representation and giving a Galois representation? We do the same thing. Oh, by the way, I'm going to say this is GL3 over E. That's an important thing. This is GU21 over Q. This is GL3 over E. So given this, we can now attach, in a similar style, Galois representation. So I'll write this out precisely. So for some, there exists number field F over Q such that for choice of prime in F, there exists unique Galois rep. There exists unique three-dimensional Galois representation over this extension of QP. This maybe is mysterious. Why do we need to have this number field? Why do we need to choose these primes? But the key thing is that this is chosen so that the determinant of the Frobenius action on this Galois representation, which is a vector space, matches the Hecker polynomial. So let me write that.
Why do you have to go to GL3 over E to attach the Galois?
It's a good question. I'm not sure. So, okay, our definition of GU21 is independent. I mean, it's defined over Q, but it depends on a choice of imaginary quadratic field E. But it's still defined over Q. I guess this is quite a crucial point. And I do think in order to define this, we need some dependence on E, and that might be why. We might just need to make this well defined.
Maybe this map there, when you take G, comma, new, and you send to G, and G is in GL3 over E.
This here. Oh, I see.
Okay, this map. How do you define this embedding? It's just take an element of U, G, U to U.
Yeah. So you'll take a matrix G new, and then this will be
To G.
G, and then here.
Just G.
Oh, but actually, when we... Oh, okay. Oh, sorry, yeah, but this is in the brackets, right? If we get rid of this...
So you say we can ignore it.
Yeah, we ignore it. You're right. And then we said that, remember that G of R is equal to the set of G new such that G was in GL3 R tensor OE. So maybe this is why we have to work with GL3E. And but I think if we didn't have that over E, then this side wouldn't depend at all on E, which I think would be a bit strange. So, okay, so let me just write what I said about, so this is defined, and by the way, from now I'm just going to call it V. We drop these subscript, but this is defined such that so for W dividing V, this is a prime of E, this is a prime of Q. Okay, I guess this is, this is Qx, where Q is P or P squared. It's the size of the residue field of E of EW, this prime, dividing V. Sorry, of when this is P. So the Hecker, yeah, I was gonna write this. This is the Hecker polynomial. So the characteristic polynomial of the Hecker operator at this prime. So this is an important thing. The way we think about this is that Euler factors match. When we think about defining L functions, we have these Euler factors. So for a modular form, the Euler factors resemble remember that quadratic polynomial I wrote down, x squared minus apx plus p to the k minus 1. That actually turns out to be this very linked to the Euler factor of the L function. So this statement, we construct this Gal representation so that Euler factors match in some sense. Okay, but then I think I don't want to say so much more about this. About this Langlands construction, because it is a bit technical and it's very strange. But I'll discuss some properties of V. Yeah, are we all happy with this? Can I rub this out? Okay, you don't have to remember the acronym, by the way. So the properties of okay. So one property is something called the de Rham property. Now I don't want to go into what this means so much because this definition comes from p-ádic Hodge theory, but I'll tell you a definition which is conjecturally equivalent. So de Rham, and sometimes we use this definition of geometric, which is conjecturally equivalent. So a geometric representation is one that has only ramifies at finitely many primes, and this is any useful representation which comes from a geometric object will have this. So for example, e.g. VF, that came from the cohomology of some variety, right? Some geometric object. So therefore is geometric. And geometric objects have, yeah, like I said, ramify at only primes, etc. And but when I write this, I want you to just think V is nice enough. V is not a very horrible representation, really bad ramification properties. It's a finite dimensional vector space, and it has good ramification properties. And this is crucial because remember we defined this H1F, this Selma group. We defined the classes which are unramified almost everywhere, and we need this sort of thing for that to make sense. Okay, but what this means is that we can attach weights to V. And these weights classify. So they're called Hodge-Tate weights. And the way we want to think about this is, for example, if V is the trivial rep, then the weights are zeros. And there are dimension V, many of these. If V is the cyclotomic character, so then the weights are, well, it's one-dimensional, so it only has weight. The weight is 1. And we can think of it as built up by things like this. So there's actually, this means that we can classify the behavior of V in terms of a set of, in this case, 3, because it's three-dimensional, a set of 3 weights. So this is extremely nice. This helps classify the different V coming from different pi. Okay. And then I'll just say one more comment about what it means to be ordinary. There's so much more I can say, but I think I'm not going to. But if anyone has questions about this, we can discuss this later, because these weights turn out to be very crucial to the theory. But okay, I guess maybe a better way to put this is that we just have a small list of numbers which have in a sense we combinatorially can think about V as it's a finite dimensional vector space, and these weights tell us what each piece looks like. So I'll maybe we'll. So we say V is ordinary if either of the following hold. So either 1 or 2 hold. So they're equivalent, but it's not obvious that they're equivalent. So the first thing is that the Hecker polynomial has a root alpha with valuation 0 at this prime above P. So this is what we saw before, right? We saw the root as a p-adic unit, therefore you can invert it as many times as you want. So this is one definition. And the second definition is this. So this is a bit weirder, but it links to this. So V restricted to this local Galois group looks like this. So we split it into 3 characters. And then it's upper triangular. So it looks like 3 characters. We don't, I mean, what's in here is important for defining V, but we don't care about it because each chi IV holds one weight. Okay, so remember we said it has 3 weights, or dimension V weights. Each of these characters hold 1 weight, which means we can think of it as powers of the cyclotomic character plus maybe some unramified character. Not plus tensor product by some unramified character. So, okay, what these weights allow us to do is, if given an ordinary V, we can actually write out what these characters are and really explicitly work with them. So, so this is a useful thing. Maybe would it help if I wrote this out for modular forms? I'll take that as a yes. It'll be very quick. It'll be 1 minute.
V here is a prime.
V E.
Of E.
Yeah, V is a prime of E.
Which it should be, so you're working on ordinary conditions, so
It's the same residue field as, or the same characteristic of the prime that you choose of the field of coefficients. This beta over P. So P is a prime over P. So
I see. There's a prime of. Yeah, hang on.
no, it's okay that we call beta P, but
No, you're right. B is a prime of a P.
over P.
Yeah.
P is a prime number which is fixed, which is
Yeah, okay. B is a.
okay.
No, you're
Absolutely right.
beta is over E. Okay.
Yeah. You know, this matches the modular forms case as well. V divides P. So prime of E dividing P. Okay, so e.g. for modular forms,
It's a prime of E. V is a prime of E.
E dividing P. Yeah. So modular forms. So F has weight K. That means it has the weights will be 0 and K minus 1. So VF, if F is ordinary, looks like psi1 and then the cyclotomic character to the power of K minus 1 times psi2 and then something here where psi I are unramified.
Here each chi is unramified. No, it's a power of
It's
atomic. Okay.
it's a power. Well, this is a result of Conrad that that crystalline. Oh, hang on, modular form. We need a condition. We need this to be crystalline for this to be true. So we need good reduction at P. Yeah, so good ordinary reduction at P. Okay, yeah, you need the good reduction as well. Then we have this result. Then every crystalline character is a power of the cyclotomic character times an unramified character, and then this turns out to be true. But yeah, this is just a detail. This is what I wanted to just explain why this is useful, because then you look, we have a very explicit form of what this representation looks like. Okay. So this was a detour. Let me rub this out.
So in this case, you were saying that the second condition in the modular form case is not true. Or
Which condition?
the second one, this one, because you have one with weight 0 and the other one is not weight.
It's weight K minus 1 because it's the cyclotomic character.
I'm just saying that
Oh, I see.
if I take this definition and I compare to the modular form, that you work, it's the same, yes?
It's the same.
Because the second condition is not true. Because you have to have all weight 1, and in the modular form you have weight 0 and something else.
No, he's saying called one weight that you one.
Oh, sorry, not weight 1. It holds one weight of the set. one of the weights.
Okay.
Sorry, yeah, okay. Pose one of. Yeah, so you have each.
Character, there are 3 weights. Each character picks exactly one of these weights. So then we know what each character looks like. Yeah, okay, I hope that clarifies. Okay, okay, and then just one last thing I want to say about those properties before I state the conjecture is this. So we have splitting of the prime in E. Okay, so P is a prime of Q, E is an imaginary quadratic field, so we have 3 cases. So case A is that P ramifies. In E, so this is a bad thing. We don't want to consider ramified primes. Case B is that P is unramified, but P splits. And then case C is that P is inert in E. So let's say in this one, P is equal to some prime of E times its conjugate. And it turns out this case is very similar to section 1. And this case has some difficulties. So what I'll do is I'll present this, and maybe we'll briefly discuss this, which is this is some results which we have in this part, and these difficulties are current work in progress. But maybe it's better if I explain to you what the difficulties are than how we solve them. Okay. Okay, so we're going to assume the following. So we're going to assume pi is ordinary, which, I mean, we can say V is ordinary. Okay. We assume P splits in E. Then we assume some minor things, minor assumptions like before. So remember we had this big image, so it's a similar thing. We assume the vanishing of some H0 cohomology groups, which actually I was discussing with Luis at the break, and he mentioned non-exceptional 0 conditions, and it's the same thing. So maybe that's, if you see something about assume non-exceptional zeros, then that's covered in this minor assumptions. So we avoid exceptional zeros of the L function. I'll keep this. This is nice. Okay. Okay, so we want to say some ideal, which is constructed algebraically, is generated by the p-ádica L function. But here's a problem. There's no p-ádica L function yet. I know. So there's some work in progress in of Eugene O, which is trying to fix this. I think he's in Princeton. But the problem is that the only known general method to construct these uses the higher heater theory of Boxer and Poloni. And so, which I can see Daniel's happy about this. So they haven't got a general theory yet. We need to wait for them to have a general theory which covers unitary groups. There's an older theory of higher heater theory for GU21, but it doesn't have maximum variation. It's in the thesis of one of Vincent's PhD students, and it gives us a p-adic L function which doesn't have 3 variables. I think it has 2 variables or 1 variable, and what this means is this L function doesn't have as many variables. Sorry, this yeah, the L function doesn't. When I say variables, I also mean the weight variables of the automorphic forms. So in this case, our automorphic form has 3 weights. Ideally we want maximum variation of this statement. Sorry, the automorphic form has 2 weights, but one of them we can twist so it's 0. So you have 2 variations of the weight of the automorphic representation, and then you just have the ZP variable. But yeah, this higher header theory, which is already existing, doesn't have full variation. So there's something which looks like the right thing, but it's not complete yet. Hopefully this will be fixed soon. When P is not split, it's a more complicated theory, and not just do we not have the L function, we actually don't know if maximal variation is achievable. So that's something to think about later. Okay, so this is working, but we can. So we don't have the p-adic L function, but we can make a good guess.
He followed this construction of Zara and David with this work of Skinner and
Yes, he's Skinner's student, so that's right. He follows Skinner's and he uses the high heater theory and the thesis of Manji, who was Vincent's student.
Yeah.
But that theory uses old ideas in high heater theory. So we need to wait the new work, and then somebody's going to start the new project, and it's.
If they are still writing this hierarchy, that
we hope they're still writing it.
Yeah.
I don't know. Yeah.
Hierarchy Coleman is fine, but
but we need high heater theory. And actually, they have this Hilbert modular forms version of high heater theory. Which deals with
real quadratic fields when prime is inert. That should actually cover this case as well. When P is inert, their theory should also work. So it's promising, but it's not published yet.
You mean this Giada paper?
I mean, no, I'm Boxer Poloni. They have Giada works with the real quadratic field when P splits. When P is inert, it's work in progress by Boxer and Poloni.
It's not online.
No, but they give a lot of talks about it.
Yeah, so
yeah, it's not online yet, so we can only hope. So that's missing for the p-adic L. But we can guess what it looks like, and the way we guess is called. Okay, we can guess using the Löffler-Zerbers construction of an Euler system for GU21. So I won't go in too much into this, but their work really does thoroughly, it defines something called an Euler system, which is designed, it's motivated in order to look like a p-adic L function. But this means we can guess. So using this, we can define some distribution, or power series if you prefer, in the Iwasawa algebra, which we want to be the L function. So we define this in conjecture that LP star is equal to some unit times LP. Okay, this is the best we can do, but actually we've made a guess already. This guess comes from the Euler system.
P is the non-constructed p-adic.
Yes. Yeah. So. But we guessed that just by after scaling this, our guess for the p-adic L function, it interpolates complex L values. Maybe that's a better way to phrase it.
But you already produced this LP star.
Hmm?
You already produced.
Yeah.
Okay.
But we don't know if this actually interpolates complex L values. We just want it to. Okay. And then we have this conjecture. sorry, we have this theorem. Okay, so let me just comment. Proving this sort of thing, it's called an explicit reciprocity law, and it's very hard. So this is very much out of reach, for example, for me. But I think there are people working on it now somewhere in the world. So we have this theorem. So this is recent work, but it uses fundamentally the work of Kazim Buyukboduk and Tadashi Ochiai from 2017. That it says, assuming the previous conditions, so I'll just say assuming the previous, which are written, I think I've rubbed them off, but so we had the V is ordinary, P splits, and then we had these minor technical things. And we have to make the assumption that this Euler system is an element of the Iwasawa cohomology. We have to assume that the Euler system is non-zero. Now we think it should be non-zero, and if the Euler system turns out to be zero, pretty much all of the work I've done becomes zero. It just equates to showing 0 divides 0, which is not. So I hope it's non-zero.
Is the consequence of this conjecture, maybe? Is the reciprocity law will imply that it's non-zero if some L value?
If some L value is non-zero, yes. But here we don't.
We mean it's non-zero as a cohomology class. So this doesn't depend on the L value, because it's zero as a cohomology. What I mean is it could be, if it's non-zero as a cohomology class, it can still project to 0 sometimes. So this sort of accounts for zeros of the L function. So this is independent.
This is stronger than.
This is a stronger result, I think.
Okay.
I think this is stronger. So we just assume the Euler system as a class is non-zero. Then we get the characteristic ideal of. Remember, we didn't use H1F for technical reasons. We're using this. I'll get rid of I won't use the V notation. So this is the dual divides LP star. And like Daniel said as well, this means that this group is a torsion lambda module. So this is part of the theorem. And then I'll write one corollary. So the corollary, if we have a character of the Iwasawa algebra, and with weights, with weights in a bounded region. So remember, we had this notion of weights which classify representations. We're just are gonna assume these weights are bounded. So yeah, this actually only works for a finite number. But okay, this is beside the point. Then if our guess for the p-ádica L function is non-zero, then our Bloch-Kato-Selmer group of gamma and V twisted by eta is finite. Okay, so bounding the Bloch-Kato-Selmer group is like, think of it as the generalization of bounding the Selmer group of an elliptic curve, which is a big part of the BSD conjecture. So yeah, assuming, again, this is also stronger than assuming the Euler system is non-zero. This is assuming it's, actually, maybe I should put eta applied to this. Sorry, yeah. The image of this element of the Iwasawa algebra under eta. Okay, so if this is non-zero, then the Bloch-Kato-Selmer group is finite. So this is a big step towards proving the Bloch-Kato conjecture, which is a generalization of the Birchman and Dye conjectures. But it would be a big step if this was the actual L function, if this was the real p-adic L function. But it's just our guess for the p-adic L function. So once someone proves this, then this will be a step towards the Bloch-Kato conjecture.
I'm confused about the notations there. So H1F
Mm-hmm.
gamma with coefficient into V twisted by eta.
Mm-hmm.
But V is a color representation over a field.
Yes. So I guess
I'm confused about the notation. What means?
it's a Galois representation. I guess here we use because this is ZP, the group algebra of this Galois group. This character has a unique restriction to a character of the Galois group. So maybe I should put this here. But then if I put this, then this also. No. It's a good question. I should clarify this.
It's okay. No,
No problem. Yeah. So this is the main result for split primes. And now, of course, we had this problem of inert primes, which was a bit more complicated. Now, I think we're pretty low on time. So maybe I'll just spend 5 minutes discussing what the problems are, and then we finish. Is that okay?
Can I ask a question?
Yeah.
Absolutely.
So let's say someone constructs the p-adical function. Will the LP star is equal to unit times p-adical function should it be a consequence of the construction itself?
So it should be a consequence of the construction of the Euler system, really. The problem with the p-adic L function is not that we haven't constructed it in maximal variation, but the Euler system is constructed to mimic what a p-adic L function should look like. So I guess this LP star comes directly from the Euler system, and it's essentially as good a guess as we can have just from the algebraic, not p-adic analytic side.
I see. So the expectation is that once we construct the p-adical function, everything else will follow.
Yeah. Once we construct the p-adic L function, we have this corollary of the Bloch-Kato-Selmer group actually being bounded.
Yeah.
I mean,
There are still more steps to do to reach the Bloch-Kato conjecture, but this is as far as the Iwasawa main conjecture would hold. Yeah. So also, maybe an important point. This is not an Iwasawa main conjecture simply because this is not the p-adic L function. So sometimes people call this Iwasawa main conjecture without the p-adic L function.
And the equality is also the conjecture here? Or?
Yeah, and the equality is also the conjecture. That's right. So with these methods of Euler systems, we only get one divisibility. We do expect it to be the equality. It seems that everyone always does this way first. And then either Chris Skinner or someone in Chris Skinner's research group, you just send them the paper and they just do the other way. And then you have an Iwasawa main conjecture.
Xinhuan?
Yeah, Xinhuan does a lot of them.
Yeah, maybe G21, something related to G21.
I don't know actually.
Working with this method
Of like congruences and.
Yeah, no,
I'm not sure.
maybe.
I guess the thing is the two divisibilities seem quite different.
Yeah.
There's no overlap in the method.
Except that maybe he was working the other.
Other side of the method. In this case.
Possibly.
Oh, you know more than something like
No, he does a lot of these. He does the other divisibility for a lot of groups. He's very good at that.
Okay, then maybe some brief words on the, and then I really will stop. Okay, so remember that when f is a modular form, and it's non-ordinary, then LP is not bounded. Okay, but also when pi is a GU21 wrap and P is inert, LP star is not bounded. And the expectation is that the p-adic L function is also not bounded, because the concept, then the definition for an ordinary thing is not compatible with induction when piece is inert. So then the problem is then LP or LP star is not in the Iwasawa algebra. Okay, so I'll briefly say there are two things we can do to fix this, and then I won't say any more about this, but perhaps if anyone's interested, we can speak later or you can email. So option one is that we find some collection of LPI in lambda, such that these construct LP. So this is one way. We just find bounded distributions which in some way, some combination of these give the p-adic L function. Then we run this theory of Iwasawa conjectures for each of these, and then you just put them together. Or the other option is that we find a bigger ring, which I'm calling lambda dash, with good theory of prime ideals. And the reason we need this is because, remember, we define this characteristic ideal as a product of primes, the height 1 primes. So this is crucial. We already know that this LP lives in the fraction field of lambda, for example, but this is no good. It's a field that doesn't have a good theory of prime ideals. Every characteristic ideal would just be 0. Then you get that every p-adic L function divides 0, which is true. So yeah, you need a ring with a good theory of prime ideals, such that LP lies in lambda dash. Okay, these are the two fixes. Now these have been done for modular forms. So I was briefly going to discuss this, but I think there's no time. But this is the plus minus theory of Antonio Ley plus others. And this is work of J. Pothast, where he cleverly constructs some ring lambda infinity, and he uses some like p-adic geometry in order to do this, but it's a ring which the L function lies in, and then he comes up with some similar statement, but it's not over lambda, it's over lambda infinity. So these are two different approaches, and they're very interesting. But it turns out for GU21 when P is inert, this one doesn't work, and this one also doesn't work. But some modified of this maybe will still work. Okay, I think that's all I will say.
So, do you have any questions?
Observation? More? No? Two? No more. So if there is no question, so let's thank again the
Thank you.
Very nice.
Thank you very much. Sorry to keep you longer than promised.